Lecture 37 is our third and final lecture on optical properties of materials. In this lecture, we talk about Raman scattering and luminescence, and then we talk about two optoelectronic devices, solar cells and light-emitting diodes. So first, students should be able to describe the processes involving Raman scattering and distinguish among different luminescent processes. For Raman scattering, the incoming incident light and the outgoing light will have different wavelengths. So for the system, when it's excited by the incoming photon, if it does get back to the same ground state, then we have so-called radial scattering. Basically, the incoming and outgoing photon have the same energy, elastic scattering. However, if there are phonon states involved at the same time, and the initial state and the final state involves different phonons, even though they are both at the ground state, then we have a different photon energy. The incoming and outgoing photons will have different photon energies, and this is so-called inelastic scattering. We can have either the so-called Stokes line that corresponds to a decrease in the photon energy, that means the generation of a phonon, or the anti-Stokes line, the photon energy is increased, that means a phonon is absorbed or annihilated in the process. So basically the photon energy difference between the incoming and outgoing photon will be the energy of a phonon. So by measuring the outgoing photon energy, we can compare that to the incident photon energy, we can determine the phonons and the energy of the phonons that we have in a particular material. For luminescence, we talked about the luminescent behavior of semiconductors previously. Direct bandgap and indirect bandgap semiconductors, they have a different behavior. And based on the type of excitation, we can have so-called photoluminescence, electroluminescence, cathodoluminescence, and chemiluminescence based on a different excitation, where they have light or electric energy or electron beam or chemical reaction to provide excitation, eventually that resulting luminescence. And if you look at the decay lifetime or the luminescence lifetime, you can have the fast process, which is fluorescence, and somewhat slower process, which is the phosphorescence. The second student learning outcome is that you should be able to describe the operation principle of a solar cell and identify important performance metrics of a solar cell with particular focus on the influence of the semiconductor bandgap. For a solar cell, in its simplest design, it's just a PN junction diode. We have a depletion region across the junction. So for the photons with energy greater than bandgap, they may be absorbed. For photocarriers generated in the neutral region, then they will diffuse around, but eventually, mostly they will recombine and will not contribute to a photocurrent. However, for photons absorbed in the depletion region that result in electron hole pair, the building electric field in the depletion region will sweep the electron holes toward different direction. That will result in a photocurrent. And note that the photocurrent is running in the opposite direction of the dark current. The dark current goes from the P side to the N side. However, for the photocurrent, it goes from N to the P, not from P to N. So they are in opposite directions. And then when the carriers are built up at the electrons building up at the N side and holes building up at the P side, that will result in potential difference, so we can have a photovoltage. If you have a low in the external circuit, that will cause a photocurrent. So that means that we have in this fourth quadrant, because the photocurrent is in the opposite direction as a dark current, now the IV characteristics will appear in the fourth quadrant. That means we are generating power. So for the performance metrics, arguably the most important one is the power conversion efficiency. That is basically the efficiency of converting the optic energy into electrical energy. So for optical power, PO shown here, then the electrical power will be current times voltage. So when you maximize the current times voltage product, you will have a maximum power output. So that's VM versus an IN. You can also use the so-called short circuit current, the current density at the current at short circuit, V equals 0, or the open circuit voltage, the voltage at which the current is 0. So you can use the short circuit current and voltage, open circuit voltage product to represent the power, but obviously that will be greater than the actual max power. So you also have the so-called field factor, which is the ratio of the max power divided by the ISC VOC product. Now, the semiconductor band gap will be important because as you reduce the band gap, you will be able to absorb more photons. You cover a broader portion in the solar spectrum. However, at the same time, the maximum voltage output will be limited by the band gap. So then now you're also going to have a trade-off between the increase of short circuit current and a decrease in open circuit voltage. So at some point, you're going to have a maximum at roughly about 1.3 electron volt for the band gap of the semiconductor. That give you a optimal efficiency of about 30%. This is so-called Shockley-Queisser limit. There are many ways to break the Shockley-Queisser limit, for example, by concentrating light or using so-called tandem cell structures. The third student learning outcome for this lecture is that you should be able to describe the operation principle of an LED and then calculate the LED emission wavelength based on the semiconductor band gap. The LED can also just be as simple as a PN junction diode. When there's no bias, there's no net current. When we apply a forward bias, you have current injection from the neutral regions. You have electrons injected from N region, holes injected from the P region. And then when we have an excess of charge carriers in the depletion region, the electron holes may recombine. And if the recombination is a radiative process, that will result in light emission. And obviously, in this case, the light emission is at the photon energy emitted will be roughly the same as a band gap. So that allows you to determine the wavelength of the light emission. And if you want to obtain different kind of wavelength emissions, red, green, blue, you just need to choose a material or design a material, semiconductor, that has a band gap corresponding to the photon energy. And if you want to get a white light, you just have to combine different kind of colors to make it white. So this is the end of the review for this lecture.